You know when you try to take a picture of a friend at a night game and they happen to be standing, like, directly in front of one of those blinding stadium
Oh
floodlights?
yeah, you usually just get a massive white glare.
Exactly, you get nothing but glare. And looking through the recent research paper from Suleiman and their team, along with the optical physics notes we gathered for you today, that frustrating photography fail is basically the core obstacle for direct exoplanet imaging. I mean, we found over 6,000 exoplanets, but never directly imaged an Earth-like one.
Right, because stars are just so incredibly bright, they completely drown out the tiny amount of light reflecting off their planets.
So, our mission today for this deep dive is to figure out if this wildly ambitious proposal, putting a giant umbrella in space to block that glare, is actually a viable way to photograph our cosmic neighbors. It is such a sci-fi concept.
It really is. But it's an incredibly optimistic approach. Historically, tackling that billion-to-one contrast ratio between a star and an Earth-like exoplanet meant we assumed we'd need an unthinkably huge, profoundly expensive telescope completely in space.
Which, takes decades and billions of dollars to build.
Exactly. But this new paper proposes a hybrid solution. We leverage existing 30 to 40 meter ground-based telescopes, like the extremely large telescope, and pair them with a 99-meter wide starshade flying tens of thousands of miles away.
Okay, so it is like having a friend hold a giant golf umbrella, miles away, perfectly positioned to block a single street lamp just so you can finally see a tiny moth fluttering right next to it.
That is actually a perfect analogy. The space starshade blocks the starlight before it ever hits Earth,
Mm.
so it lets the planet's faint reflected light pass undisturbed straight into the telescope's lens.
Right, so you're moving the light blocking problem off the telescope entirely and putting it out in the vacuum of space.
Precisely. Now, if you look at the design of the starshade itself, it's not just a big circle. It's shaped like a giant, complex sunflower.
Wait, why a sunflower shape? I mean, why not just use a giant, simple circular disc? That seems a lot easier to build.
Well, you would think so, but if you block light with a perfectly round disk, diffraction actually bends the light waves around the edges.
Oh, right, because light acts like a wave.
Exactly. And those waves crash together right in the center behind the disk. It creates a blinding bright spotlight right where you want the deepest shadow, which is called the spot of Aroga.
That sounds like the exact opposite of what we want. So how does the sunflower design fix that physics problem?
Well, by adding those mathematically precise cuddles around the edge, the starshade actively manages that diffraction. The varying edges prevent the light waves from constructively interfering in the center, which creates an incredibly deep shadow.
Wow, so it essentially cancels out the glare.
Yeah, effectively reducing the starlight by a factor of 10 billion.
That is wild. But let's look at the reality of keeping the camera on the ground. I mean, even if you block the star perfectly in space, your lens is still sitting under our planet's turbulent atmosphere. Isn't it like looking at a penny through the bottom of a moving swimming pool?
It is, and that atmospheric blurring is a huge challenge. But this setup handles it using advanced adaptive optics.
Right, the lasers.
Yeah, ground facilities shoot lasers into the sky to measure the atmospheric turbulence in real time. Then, computer-controlled mirrors physically deform thousands of times a second to perfectly cancel out that blur.
That is just insane engineering.
It really is. We can essentially untwinkle the stars, matching the crispness of a space telescope, but with massive light-gathering power.
And obviously, processing the massive amounts of data required to deform those telescope mirrors in real time relies heavily on AI and machine learning, which actually brings up a great point for you listening. If you're looking to optimize complex systems and need help uncovering where AI agents could make the most impact for your business, you should check out our sponsor, Silk.
Yeah, they do great work.
They really do. Whether it's AI training, automation, or software development, head over to embersilk.com.
So getting back to the ultimate capability of the
Yeah.
system, the payoff is staggering. Looking at targets up to 7 parsecs away, this hybrid setup could capture the reflected light of an Earth twin exoplanet.
Wow, a literal twin.
Yes, and in just a single 1-hour exposure, we could analyze the light spectrum and actually detect the signatures of oxygen and water.
Wait, really? Just 1 hour?
Just 1 hour.
Getting a viable spectrum in 1 hour is a massive leap forward. I mean, we aren't just logging transit dips anymore. We're figuring out how to peek right around the star to see the planetary atmosphere itself.
It changes the entire paradigm of how we approach these grand astronomical challenges.
It's an incredible display of human ingenuity. We are so close to proving we aren't alone out there. So if you enjoyed this deep dive, please subscribe to the show. Hey, leave us a 5-star review if you can. It really does help get the word out. Thanks for tuning in.
Thanks, everyone.
And I want to leave you with a thought to mull over. Consider the wonderful paradox here. Our ultimate space discovery, finding a second Earth out in the cosmos, might actually be achieved by keeping our most powerful cameras firmly planted in the dirt right here on our first one. The future of exploring the universe might just be a brilliant collaboration between the ground beneath our feet and the stars above.